we're going to be talking, actually, we're going to be going through our Pset 2 solutions. So a lot of these are kind of figures and drawings, so I want to go through this together. So we need to draw the primitive lattice basis. So this is going to be, so if I have these vectors, again, I'll have a kind of this square cell, and that will have one primitive atom, or one atom. I could also do here, this cell will have like a parallelogram type cell. Here we have this kind of cell right here. So again, this hexagonal unit cell. Here we have cell here, cell here. We can do here, and then finally this rectangular cell here. And if you draw, you see that each of these corner atoms are going to share basically kind of a fourth. So you can see here. So here it's shared by 1, 2, 3, 4. There we go. So that's 1. So look at the 5 lattices, draw the primitive lattice for each basis. All right. 2, determine what type of conventional unit cell is represented in A, B, and C. And C, how many atoms are in each unit cell? What is the atomic packing factor for each unit cell? Well, for A, I know this is simple cubic. I know this is BCC. This is CC. I know for my that this is going to be 1 atom, and the packing factor is going to be 5 or 6. This is going to be 2 atoms. This is going to be 0.68-ish, again, from our notes. And then this is going to have 4 atoms, and this is going to have atomic packing factor. So atoms, and this is going to be APF. There we go. So exactly, that's kind of, again, just from our notes. Determine the directions in A. What are the planes in B and C? Are any directions close-packed? Are any crystallographically equivalent? What about the planes? Prove quantitatively. Are any planes close-packed? What are the close-packed planes for each unit cell? Well, let's see. We know that to have a close-packed plane, our structure must be close-packed. So this is the only close-packed structure. So the close-packed plane here is going to be my 1, 1, 1 family of planes. So there's no close-packed planes in here. There are some close-packed, there are some close-packed directions here. So the close-packed directions would be 1, 0, 0, that family. Here would be the 1, 1, 1, and close-packed here are 1, 1, 0. So we do have some close-packed directions that can occur in each of these cells. So let's kind of figure out the directions, let's figure out the planes, and let's see if any of our crystallographically equivalent. So I can look here. So let's go ahead and do this example right here. So this is just going to be the, again, so I could do my 1, 0, 1 finish minus the start, which is going to be 0, 0, 1. So this is going to be my 1, 0, 0 direction. I'm going to change colors here. So let's go over here. This is going to be 1, 1, 0 direction. We start from the origin. Let's go, how about here? So here I have my finish vector is at 0, 1, 0. My start is going to be 0, 1, 1. So my finish, or my final vector is 0, 1 hat, 0, 1, 1 hat. And then finally, let's go gray over here. Let's kind of go up, scroll up here for a little bit. Let's go a little bit further. So my finish is going to be at 1 half, 0. My start is going to be at 0, 1, 1. So I'm going to be left with a half, 1 half hat, and then hat. And I'm going to, again, I need to make that, multiply that out to the integer values. So it's going to be 1, 1 hat, 2 hat. There we go. So let's go ahead and so we've got all the directions there. So let's go ahead and now do the planes. Well, what's our protocol for our planes? So I want to take this over here. What are my intercepts? It's going to be x is infinity, or parallel, y is infinity, and z is equal to half. So I do the reciprocal, so it's going to be 0, 0, 2. That's it. And let's go ahead and do this plane right here. So crossing through my origin, so I need to pick a new origin, O prime. So let me try this. What are those intercepts? Do we intersect the x-axis? So our new x, yes, at -1. Y, no, that's going to be infinity. And z, yes, at 1. So then our plane is going to be, sorry for this, it is going to be -1, 0, or actually 0, 1 hat, 0, 1. And now let's go to our planar density calculation. The crystallographic equivalent directions are going to be this one and this one. So again, because they're that family, right? The 1, 1, 0, actually the group, so you kind of see here and here. So they're going to be crystallographically equivalent directions, pass the same number of atoms, same magnitude, and those are the only ones. Are any planes equivalent? No. None of those planes are close packed as well. So we could prove this quantitatively again by calculating the packing, actually the density. So let's actually calculate the planar density. Planar density for this atom. So here in this plane, we have, this is going to be A and A, and we have one atom here. So the planar density is going to be one atom, so pi r squared divided by A squared. And where A is equal to what for BCC structure? Well, that's going to be equal to 4r square root of 3. So you can calculate that out, and that's not going to be a close packed plane. What about this one here? Well, let's go ahead and draw this one out. So I'm going to do a little delete here. So let's go over here. So if I project this plane, so now remember that this distance here is going to be 4r. This distance here is going to be our A. And I have atoms here, 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 and face. So what's my PD equation? How many atoms? So 1, 2, or quarter. And then what else? I have half there. So I have 2 atoms. So 2 pi r squared divided by, again, 4r times A, where A is equal to 2 root 2 r. So you can prove that that is not a close packed plane. All right, so let's go ahead and start drawing some directions now. So I want you to draw the following directions in the empty unit cell below. So I need to figure out 3, 1, 2, 1, 2, 1, 2. Here we go. So let's go ahead and let's start kind of drawing this out. So let's go ahead and start with this direction first. So I need to create this 1, 2, and then 0. So my finish vector, I'm going to start off at essentially, let's go ahead and let's kind of figure out how to draw this. So I want to start at 1. Actually, I want my intersection to be a half, 1, actually half, 0, 0. And then I want to, that's my finish, and I want to end at 0, 1, 0. So if I draw that here, so let's draw that direction. I'm going to keep it in green. So if I do 1/2, so that's going to be this point right here. Oops, excuse me. So 1/2, 0, 0, and then my start is going to be at right here. So 0, 1, so right here. That direction. So finish minus start. What does that leave me? 1/2, 1, 0. That's equal to 1, 2, 0. What about this one? So let's draw this. So now I want 1, 1 hat, 2 hat. So I could do the same thing. So I want my finish to be 1, this to be 0. Actually, excuse me. I need this to be, because I need my trick. So I need this to be a half. I need this to be basically 0, and then I need this to be 0. And then we're going to go to 1. Actually, no, excuse me. It's going to be 0, 1, half, and it's going to be 1. So let's go ahead and set that out and make sure that all works. So we get half, we get 1/2 hat, and then we get 1. And you multiply that out, so it's going to be 1, 1 hat, and 2 hat. So we're going to have that same finish here, and then we are going to go from 0, 1/2, and then 1. So we're going to start here, we're going to go right there. Perfect. And then finally, let's go ahead and get this, let's see if we can get this guy. This one's a little bit more complicated, so let's go ahead and do a 3/2, 3, 1, 2. So if I want to, actually let me change my colors here just a little bit. So 3, 1, 2. 3, 1, 2. Let's figure that out. So I'm going to need this to be this direction. We're going to have the following intercepts. So 1/6, actually, excuse me, 1/2, 1/6, and then 1/3, and then minus. That's going to be a finish. This is going to be our start. So that's going to give us a half, half, half. So we need to multiply by 6. So that's going to give us 3. That's going to give us 1, and that's going to give us 2. So I need to do starting from here and finish at a half, basically a 1/6, and then a 1/3. So we're going to go like basically up to here. So that's that direction. So draw those intercepts. Now we're asked to draw 3, 0, 1 and 0, -1, 1. So defining our origin. So let's go ahead and do this one first. So 3, 0, 1. So these are my 3, 0, 1. So my intercepts are the inverse. So I'm going to have an x-intercept of a 1/3, y-intercept that's always parallel, so infinite, and then a z-intercept of equal to 1. So I know it's going to intersect my z parallel here. My x is going to be at a 1/3 here. So I'm just going to draw right this, this, and we're good. So next one is going to be 0, -1, 1. 0, 1/2, and 1. So let's go ahead and do this one. So let me get my drawing right here. So now we have this kind of, again, let's go ahead and write our intercepts. So x, y, and z. So we know that this is going to be infinite because, again, it's x is equal to 1 over our h value. So 1 over that is going to be infinite. This is going to be -1, and z is going to be equal to 1. So if we're doing a -1, we want to set up, let's go ahead and set up our kind of new coordinate system. I'm going to call this O prime for this particular plane. So let's go ahead and set up our new coordinate system like this. So if I want to intersect, so I know I'm going to intersect at z equals 1. I'm going to intercept, again, this is my xy, this is my y at -1 here. So I'm going to connect these here, these here, these here. Let's go ahead, kind of connect them here. I'm going to draw that plane like so. So you can see here, I'm never intersecting this x, my new x coordinate system, or my x, h, k, l. Y is going to be intersected at -1. So there it is. Those are your planes. So you need to make sure to define your origin. Again, I used the original origin for the first problem. I had to redefine it for the next one. All right, last problem. I'm interviewing at Vandelay Industries. They gave me the following RDF PDF graph. Is this a metal, polymer, liquid? Draw the other polymers. So let's look at this kind of graph first. So I know for sure that this is a metal. No question about it. The other plots, so if I'm doing a polymer, it's going to look like this. And again, it could be different for semi-crystalline polymer if it's a gas. I just have my flat line. So G of R, same thing, R, G of R, and it's going to be flat line there. All right, so we know now metal, polymer, liquid, glass. What specific element material is represented by the PDF below? This material has 12 nearest neighbors. So if this material has 12 nearest neighbors, I know that this, basically the integral of this peak, the integrate from this peak is equal to 12. Excuse me here. And so if we integrate this peak, then we're going to get 12. So if there's 12 nearest neighbors, I know that this material, this structure, is going to be FCC, the 12 nearest neighbors. So if I know that this is FCC, I know that this is 2R, and then this is going to be A, which is going to be 2R root 2. How do I know this? Well, let's go back to our lecture 2 notes that we've kind of gone through here. So I know it's 2 root 2R. So let's go ahead and look back at our, again, we can look at this table here. So 2 root 2R, and let's go back to our FCC as well, this derivation, 2 root 2R. That's it. So I can now do some math. Oh, excuse me. So let's go back to our Pset 2. So Pset 2, let's go back down here. So if I know that basically 3.53 angstroms equals 2r square root of 2. So now I could go ahead and solve for r and then fill in what this is. So let's go ahead. I'm going to switch my writing style for a second. I'm going to create a new notebook. Apologize for this. If you're interested in entering 110, I have a separate playlist for that. So I need to solve for, let's go ahead and look at this, 3.535, set it equal to 2 times r times square root of 2, and solve that for r, and we get a radius of 1.24. Again, so twice that would be the last point there. So the first kind of point there would be 2 times this. So let's look 1.25 basically. So let's look at our periodic table. So we need a metal that is FCC. So I need to look at the little dot that has a radius of covalent radius. I need a metallic radius of, oh, that's 1.28. Nickel. You can see right here, nickel has a radius of 1.25. So fantastic. Oops, excuse me. So now we know that this material is, let's go back to Pset 2. This material is nickel, and it has an atomic radius of 1.25. So nickel, which is FCC, let's just double check that. Nickel is FCC, and it's 1.25. So that is problem set 2. So please let me know if you have any questions, and hopefully you did excellent in this problem set. Thanks. Have a good one. Bye.